Dear students, welcome to the online class. I am Dr. SSC Hiramat. In this video, you are going to study about the thermodynamic treatment of Le-Chatelier's principle. Now, consider a reversible reaction. Consider a reversible reaction. That is, A molecules of A reacts with B molecules of B reversibly to give M molecules of M and N molecules of N, and Kp is the equilibrium constant, and delta H is suppose negative X kilojoules, and delta N is suppose that is -1. Here delta H is the enthalpy change and delta N is the number of moles of gaseous products minus number of moles of gaseous reactants. Now, the Le-Chatelier's principle may be stated as, for a reversible reaction at equilibrium, if it is disturbed by the change of temperature, pressure or composition, the equilibrium is shifted in that direction in which the effect is nullified. For example, in this reaction, suppose this is one exothermic reaction, delta H is minus. Then, if the temperature is decreased, equilibrium shifts in the forward direction. And another way about the composition, if the number of moles of gaseous products are less than the number of moles of gaseous reactants, then with the increase of pressure, equilibrium shifts in the forward direction. In that way, the equilibrium is shifted in that direction in which the effect is nullified. Now, this can be verified or proved thermodynamically. Now, suppose delta G is the enthalpy change of the reaction, free energy change of the reaction. We may take here the enthalpy or free energy, which is the function of temperature, pressure and the extent of reaction. Delta G is the free energy change of the reaction, and which is the function of temperature, pressure and extent of reaction, where that is G is the extent of reaction. Means higher the extent of reaction, more will be the Kp of the reaction. Okay, like this G indicates the extent of reaction. Now, on partial differentiation of this equation, on partial differentiation we get partial differentiation of this is d delta G as it is, because there is only one term. Then d of delta G with respect to T at constant temperature and pressure. At constant pressure and epsilon into dt. Means, as in the case of the partial molar quantities, we can differentiate this in this way. Plus dou by dou P of delta G at constant, that is temperature and epsilon into dP, Second term means you keep the first term, keep P and G constant and differentiate with respect to T. And in second term, you keep T and epsilon, that is G constant, and differentiate with respect to P, plus dou by dou G of delta G at constant temperature and pressure, then dou G. Suppose this is equation 1. This is equation 1. We know delta G is equal to dou G divided by dou G. Dou G divided by dou G at constant temperature and pressure. This is by definition of chemical potential. Means the ratio of change in free energy with respect to a small change in the number of moles of components, that is the free energy change, that is the chemical potential. Now we can substitute this by this term. Okay, then equation 1 becomes d by delta G, the same as it is equal to dou by dou T, you keep it as it is, and dou G by dou G at constant temperature and pressure, and this term is at a constant pressure and G and dt. You substitute delta G by this term. Similarly, dou by dou P into bracket, that is you substitute delta G equal to D, that is dou G divided by dou C at constant temperature and pressure, and this is at constant temperature and D and dP, plus here also we substitute the same dou bar dou G, that is dou G by dou C at constant temperature and pressure, this is dou G. Suppose this is equation 2. Now here we can make a mathematical change, means differentiate with respect to G first, then with the temperature. In that way we can rearrange this equation 2 may be rearranged by sequence of differentiation. Then we get d of delta G is equal to dou by dou G, then you take dou G divided by dou T, then this at constant pressure and epsilon, that is G, and this is at a constant temperature and pressure, and dt. Just you change dg by dt, that is dou g by dou t. Then automatically this term remains same, plus dou g by dou g divided by dou p at constant temperature and g, and this is equal to, this is at a constant temperature and pressure, then it becomes dp, plus this term remains as it is, that is dou by dou g into bracket dou g by dou g at both are temperature and pressure are constant. We may use the both temperature and constant both in the outside. Suppose this is equation 3. Now dou g divided by dou t from equation dg equal to v dp minus s dt. Okay, we may rearrange, that is dou g divided by dou t is equal to dou g divided by dou t equal to minus s, that is dou g divided by dou p equal to minus s. Then similarly dou g divided by dou p at, this is at a constant pressure and this is at a constant temperature, equal to v, then we may take g, that is dou divided by dou g into bracket dou g divided by dou c at constant temperature and pressure may be represented as g double dash, that is double differentiation. The same differentiations are there, thus we may write. Then equation 3 becomes that is dou d delta g equal to dou g, this term dou g divided by dou t is equal to minus s, this is equal to s, and we may take this minus, and this totally, this term is at constant temperature and pressure, and this is equal to dt, plus dou by dou c, then dg by dp at constant t and epsilon, t is equal to v, that is equal to v. This is at a constant temperature and pressure into Tp. Okay, constant temperature and pressure, that is Tp, plus G double dash d epsilon. Suppose this is equation 4. Now S divided by dou G at constant temperature and pressure. It is nothing but delta S. Delta S. Similarly, dou V divided by dou G at constant temperature and pressure, that is equal to delta V. Then equation 4 becomes d delta G is equal to minus delta S into dt plus dV equal to delta V into dP plus G double dash into epsilon, that is G dG. This is equation 5. This is equation. If we consider a case at T, P and G are varied such that the equilibrium is maintained. Then delta G becomes equal to 0. Then D of delta G also becomes 0. Then equation 5 becomes this term becomes 0. Then the equation 5 becomes minus S dt plus delta V dP plus G double dash dG is equal to 0. So this is equation 6. In equation 6, G double dash is nothing but dou square G divided by dou G square at a constant temperature and pressure is positive as G is delta G is delta G is minimum. And by definition, delta S equal to delta H divided by T. Then equation 6 becomes this is equal to delta H divided by T, delta H divided by T into dt plus V delta V into dP plus G double dash dG is equal to 0. Equation 7. Equation 7 may be applied for the different cases. Equation 7 may be applied for different cases. Let us study about the application of equation 7 to the various cases. Case A, that is variation of G with temperature T at constant P at equilibrium. When P is constant, dP becomes equal to 0. Then equation 7 becomes minus delta H divided by T into dt plus G double dash dG is equal to 0. So this is equation 7. 8. On rearrangement of equation 8, we get, suppose this dou G divided by dou T, that is dou G divided by dou T at constant pressure, because we are applying at the constant pressure. This is equal to delta H divided by T. Here G double dash is a positive quantity. Then the sign of dou G depends upon sign of delta H, sign of delta H. For exothermic reactions, delta H is negative, equal to 0. Hence, dou G divided by dou T at a constant pressure, negative. Okay, that is T. G decreases in exothermic reactions. Then with increase of T, G increases in endothermic reactions. Then third one, with decrease of T, G increases, then it is decreases, G decreases in endothermic reactions. Then with decrease of T, epsilon increases in exothermic reactions. In this way, we can apply 1, 2, 3, and 4 in the case of variation of temperature at constant pressure. When T is constant, dt is equal to 0. dt is equal to 0. Then equation 7 becomes equation 7 becomes delta V into dP plus G double dash d G is equal to 0. On rearrangement, we get dou G divided by dou P at constant temperature, that is equal to delta P divided by G double dash at constant T, as G double dash is a positive quantity, the sign of G depends upon sign of delta V. Now first, and delta V is equal to 0, that is delta N is also equal to 0, that is V of products is equal to V of reactants. V of products is equal to V of reactants. Then epsilon is independent of T, independent of P at constant P. Then second one, and delta V is positive. Delta N also positive. Then products is greater than reactants. Products is greater than reactants. Then epsilon increases with decrease of P. Decrease of P. Then third one, then decreases with increase of P. Then fourth one, when delta V is negative, that is delta N is also negative. Then in that case this is negative, means products must be less than volume of the reactants. Volume of the reactants. Then as it is negative, it increases. Then fifth one, decreases